Hello everyone. We're again talking about complex differential geometry. Last time we started talking about complex structures on complex vector spaces, and complex vector spaces are um, related to the complex manifold. We had that manifold M, and since it's a complex manifold, um, we could take a little open set on this manifold, and then it would be homeomorphic, to a copy of Cm, which would make it an m-dimensional manifold, m-dimensional. So today we're going to continue talking about this complex structure um, called J on a complex vector space that turns a real vector space into a complex vector space. So before we do that, let's recap briefly what we did last time. So one, okay, let's say summary or recap. First of all, we talked about the complex structure, J. We said that J squared is the same thing as the negative of the identity map of a vector space V to a to itself. So this is a vector space, a real vector space. And then we showed that, um, well, we defined a complex vector space as a real vector space plus the complex structure. So if the real vector space admits a complex structure, then the real vector space turns into a complex vector space. And then thirdly, we showed that this definition of a complex vector space is equivalent to the notion of a vector space over C. And once we established that, we were looking at some interesting results on such spaces that have a complex structure. The first thing that we looked at, let me scroll down to find it, um, is that sub one is that we induced a complex structure J star on the dual space V star. And number two, we showed this really interesting result that the eigenvalues of J are plus minus I, and they come in pairs. That one was our first theorem that required a lot of um, sub statements and um, a lot of proofs, but mainly we figured it out using something called a minimal polynomial, which is a polynomial in the matrix for J that it's the smallest order polynomial in the matrix for J, which gives you 0, which in J's case was matrix J squared plus 1 is equal to 0. And so from here, we reason that since it doesn't have any repeated roots, the theorem says that we can form this eigenspace, and then we showed that the values are plus and minus I because of the um, relationship of j squared is equal to minus 1 and or minus the identity. So that gave us plus minus I. And lastly, that we use the conjugate root theorem. Yeah, the conjugate root theorem to show that they come in pairs. So that's uh, the last thing that we did. We had some corollaries. Firstly, that um, complex vector spaces are always even dimensional. Because this only works when you have pairs of eigenvalues, and if you have pairs of eigenvalues and you can construct an eigenspace from with pairs of eigenvectors, well, each pair has two, so the total dimension has to be a multiple of two, therefore even dimensional. And that we always have an eigenbasis. Basis for J. All right, so that's what we did last time. And so today we will continue talking about uh, J and its matrix form. Okay. Wait a minute. Yeah. Fine. Good. The first thing that we're going to look at is the matrix form of J star. So we already found that um, so we already talked about the matrix form J in the basis B. We're going to show that we're going to try to find what the matrix form of J star will be in the same, well, in the basis that's dual to B. We'll call that B star. So B star is, right. In fact, let's define it. B star is defined as the covector basis R equals 1 to M, where, uh, right, where you have this relationship. S, that's fine. Delta RS. So this is the dual basis of the basis that we were using for, so these are the basis vectors from B. So that's B star. So it's the dual basis to B. Um, right. So what we're going to show is that J star is the transpose of J. So let's start with the definition. So J star is defined to be J star acting on alpha, inner producted with V is equal to J acting on V, inner producted with alpha. That's how we used our previous definitions in order to leverage this definition. So we know that this inner product is equivalent to alpha acting on J acting on V. So just in general, if we have an inner product of this type, then this is equivalent to saying that this is alpha acting on V. So in this case, alpha is the same, but we know that J is going to take V and it's going to spit out another vector. And so whatever vector is the result of that, that's what we're plugging into alpha. So you could also think of this as alpha after J of V. You can also think of it like that. So if we continue with that, now we're going to decompose it in the dual basis, alpha R, epsilon R. So this is where kind of the stuff that we talked about, tangent spaces and cotangent spaces start to come in and their coordinate bases. Um, and then we already know about the matrix form of J. So we're going to decompose it like that. And then if we take the coordinate, um, right, so then we also take the coordinates of the vector, and then, yeah, okay. Then we're using the fact that, so this would be equivalent to epsilon r acting on ES. So we could think of this as acting on this basis vector. These are all essentially numbers or scalars. So we can take these out. So if we take them out, then we get alpha r j b. I'm going to put a little parenthesis outside of this. Then we have the indices. Vj is also just a coefficient. And then you got epsilon r ek, which if we simplify that, let me write it like this. So then that will give us delta rk. I'm just rewriting all of the elements here. J R V J. Right. So then what we did was we again used the Kronecker delta to collapse the indices. Wherever we saw a K, we would replace that with an R. So the K was over here. So we replaced that K with an R. Um, that gives us overall. Now this is okay. So we recognize this index equation. If we look at this index equation, it's a matrix that's acting on a row vector or a covector. Um, so we can think of this as this kind of thing. It's but then transposed alpha. Oh, is that right? My right. Okay. So then we get that, and we're bringing back the other side of the equation. Um, so we bring back the other side of the equation, then we get J star in the basis B star acting on alpha is equal to V J B transpose acting on alpha. And then again, we're going to use the same idea that we used last time, which is that V is arbitrary. Since V is arbitrary, we know that it must be that these two are the same. So then alpha is also arbitrary. Alpha is also arbitrary. So then we can equate the matrix elements with each other. So then that gives us J star in B star is equal to J B transposed. Okay, so in the notes, I wrote it out as matrices, and then I also wrote it out as the elements of the matrix. We know that matrix equality is the same thing as element-wise equality, so those are the same statements. So this tells us that the matrix of J star is the matrix of J, but transposed. So that's our first result. I'm going to put a little star over here. So next, uh, we're going to move over to since we know that J star has eigenvalues plus minus I. So that means that its eigenvalues come from C, right? So it's more convenient to work from now on in V star tensor product C, um, or direct product with C. So in this, so this is a real vector space. Is it? Um, J star has, yeah, because J star, trying to convince myself. So J star is going from V star to V star, and V star is the dual basis to V, and V is a real vector space with a complex structure, which makes it a complex vector space. So yeah. So this is something called the complexification of V star. So this is equivalent to, so let's bring that down a little bit so that we can work with it. This is isomorphic to V star plus I V star. So like, I'm not sure if this notation is exactly kosher. I've seen it, some people write it this way. Basically, you have one element from V star plus I into another element from V star. So very analogous to the way that we write complex numbers, which you would might say is R O plus I R. That would be isomorphic to um, C. And the I kind of reminds you that you can't mix the first R with the second R. Okay, so now let's take an element from that space. Let's say that lambda is an element of V star O cross C, which means that we can write lambda as alpha plus I beta, where alpha and beta are elements of V star. So now J is, sorry, this should be J star, right? J star is a map that goes from V star to V star. So this is not uh, actually defined on a complex on the complexification. So we need to extend it again. We need to take what we defined earlier and we pull it to the new context by extending it. So we're using the earlier definition as that building block that is going to be slot together to make the new definition. So how do we do that this time? So J star of lambda is going to be by definition equal to J star of alpha plus I into J star of beta. That's how we're going to define it. So J star is defined on V star, which means that this is well defined. And again, because it's defined on V star, this is also well defined. And overall, this will be an element of V star O cross C. So from here, we can obtain two, uh, right. So we're talking about this space, V star O times C. This forms two subspaces in our space. So J star, and it's using J star. So J star separates our space into, okay, well, I'll draw the diagram because it's not exactly partitioning it into two parts. It's kind of isolating two smaller regions, but we'll get into it. um, to two kind of building blocks. Those are called, where we're going to call them VC star and VC star star bar or bar star. And the elements of these, so okay, so what are these spaces? Um, this is the space of elements which if you apply J star on an element from here, then you get plus I into V. So this is the eigenspace of J star that corresponds to the eigenvalue of plus I. And you can figure out what this one's going to be. Analogously, this is when J star is acting on W, then this should give us minus I into W. So these are the two eigenspaces of J star, and we're going to be able to use these on to break up V star cross C into two building blocks. That's going to give us the whole of V star cross C again. So uh, we know that yeah. So these are called the elements of type 1, 0. And these are called the elements of type 0, 1. And one note here, in Chernchen and Lamb, these are called VC and VC star. Sorry, VC bar. I added the star because these are actually related to V star. And so it's reminding us that what we have in these spaces are covectors and not vectors. So that's something that is not standard notation, and you can always use VC and VC bar if you'd like. But I just wanted to remind everyone in the notation that these are spaces of covectors. One interesting thing about this space is that the only intersection between VC star and VC bar star is actually the zero vector. Because think about it, if there's equation 1 and there's equation 2, the only V and W that would satisfy both of these equations is the zero vector. So that kind of tells us the shape of these two as a Venn diagram. They kind of look like this, where I'll do that in a different color. There's only one point here, which is 0. That's their intersection point. And you have one, which is VC star, and the other one, which is VC bar star. And these are the two eigenspaces of J. Now, the mind you that all of V star cross C, let me draw that out first. So let's say that this is V star cross C. It's bigger than this. And a nicer way to draw this actually is like that, like this. If you've read the notes, you've already seen this diagram. Uh, there's no reason why I switched to making it square. It's just that it's an easier way to draw it. It's the same diagram. That's your point 0. And then let's say that this is V bar star C. I'm going to say all of the little accents on this in different orders in different times. You're going to have to bear with me on that. Uh, yeah, and that's VC star. So there's what I would like to point out from this image is there's a lot of uh, this whole big square is in the Venn diagram is V star cross C. And there's a lot of V star cross C that isn't purely either of these subspaces. So that's why I wanted to avoid saying that it's built up of two subspaces. But it's there. It uses those building blocks. So remember that the elements of V star cross C look something like alpha plus I beta. But you can also construct them from uh, these two. Yeah, so that's what we're going to get to next. So that's the next interesting result is that V star O cross C is isomorphic to VC star O plus VC star bar. We're going to show this. So this is the next result. Okay, so let's start with, I'm going to put an underline on that. That's the title of this part. Um, J star of lambda is equal to J star of alpha plus I. So this is by definition, J star beta. Remember, lambda is still equal to alpha plus I beta. And alpha and beta are both from V star. And lambda is from V star cross C. So since lambda is an element of VC, oh, right. So what now we're going to refine this. So we're going to say that lambda is an element of VC star. That means that J star of lambda is equal to I lambda. So let's expand that out using the definition. J star of alpha plus I J star of beta is equal to I into, and then we expand out the definition of lambda to alpha plus I beta. And we know how to evaluate this. So this is equal to I alpha minus beta. Did I get that right? Yeah. And so if we compare the two sides, we know that for complex numbers, you can't mix them. You can't mix the two sides. So we can read off the coefficients of the I and the coefficients of the term that does not multiply by I. So that means that J star of alpha is equal to minus beta. And J star of beta is equal to alpha. Yeah, that's right. So let's take lambda bar. Lambda bar, by definition, is equal to alpha minus I beta. It is the complex conjugate, but in this situation, these are both elements of V star. So I thought it'd be pertinent to make it explicit. Um, so let's see what happens to this when we use J star on it. J star of alpha minus I beta is equal to minus alpha. So this is J star is linear, so we can distribute it over all of the elements. Then what will happen is we will get J star of beta is equal to alpha. Okay, let me just write it the way I wrote it in the notes. There's some factoring that I did here. I wanted to undo that, but suffice it to say, what you'll get is, I think there's a minus I here. Yeah. Um, and so you get uh, minus I lambda bar. You can check the calculation, but yeah. So that means that if lambda was an element of VC star, then lambda bar, as defined here, would be an element of VC star bar. And that's why we named it VC star bar. Right. So that's the first result that we're going to need in order to prove the second one, which is that, yeah. So here's the decomposition of V star cross C. Before we get to it, um, yeah, we know that lambda I equals 1 to n, uh, and gonna check something here. Lambda bar I equals 1 to, would this be n? No, I think this will be m. These are two, these are two covector bases. And together, so if we take their union, then we get this set, lambda I, lambda bar I, where one less than I less than or equal to m. This is that eigenbasis that we were talking about, that we were guaranteed to get from the last time. Uh, so we're going to call this eigenbasis curly L. This is not the Lagrangian this time. This is the basis of eigenvectors for V star or V star cross C. So right. So the next one, so this is the what we wanted to prove. So decomposition of V star cross C. Okay, first of all, let's let F be an element of, let's call it phi, because I did say that I'm going to use Greek letters for all the covectors. So phi is an element of V star O times C. Notice that we can decompose it into phi 1, which is equal to half phi minus I into j of phi, and phi 2, which is equal to half phi plus I j of phi. And if without, like, I know that these are two very complicated expressions that I just wrote, but notice that phi is equal to phi 1 plus phi 2. No matter what phi is, as long as phi is an element of V star cross C, we can write it this way. And you don't even need to compute anything. You can just see that these two will cancel out and these two will add up. And half phi plus half phi will give you phi, right? So that is how we're saying this. So notice that phi 1, if we plug that into J star, I'm noticing that there's a lot of points in the notes where I forgot to turn J into J star. I'm going to fix that next time. So J star of phi 1 is equal to I into phi 1. Let's see if we can work that out. So J star, I'll work out one of them. We'll leave the other one. Half phi minus I, half, or I by 2, let's say, j of phi, but this should also be j star. J star of phi. So what we know that we got half j star of phi. So we're using the linearity here again. minus I by 2 j star squared of phi. Ooh, j star squared of phi, that's interesting. If we get j star squared of phi, then what does that give us? That gives us the negative, or let me just isolate this much. That's the negative of phi, right? By definition. So we get half j star phi. Right, let's evaluate this j star of phi as well. So, hmm, okay, let's leave that for now. J star of phi minus plus I by 2 phi. So phi is an element of V star cross C. If someone can figure out what I'm missing here, feel free to shout it out or put it in the comments because I didn't uh prepare to do this, but I wanted to see if we could show it. Um, J star of phi, we don't know that J star of phi is I by I phi though, right? But that seems like what it's supposed to be. Maybe I'm forgetting why this should be I phi. So then if that's I by 2 phi plus I by 2 phi, that gives us the right answer. I'm going to check that, but I think that's right. That gives us I phi as what we needed. Okay, I will try to do the math again uh and we'll confirm it. But what we should be getting is I times phi 1. Should be getting I times phi 1. So, and if we take J star on phi 2, then we should get minus I into phi 2, which means that this is an element of V bar, or sorry, this is an element of V star C, and this is an element of V star C bar. Okay, I'll do the math again and I'll post it on the Discord, but this is what it should come out to. Um, right. And so I think I jumped the gun a little bit with um, the diagram. Let me bring that up again. So now this makes more sense. We copy this back to where we were. Okay, I'll just draw it again. So okay, we got lost in the sauce a little bit. So let me recap what we just did. We showed that so this is any element of V star cross C, right? And we showed that this is an element of VC star, and this is an element of VC star bar, which means that for any element phi, we can uh, decompose it in terms of these two subspaces. So that's what I meant when I said that these are the building blocks. So let's say that this is the subspace VC star, and this is the subspace VC star bar, and this whole square or rectangle, or whatever way you draw it, is V star cross C. And if we wanted to, oh, right, and this one point is 0. If we wanted to get to any point here, we could always add a point from each of these, and adding them would get us to any point here. So you could think of it as acting like a basis for the entire set. In fact, that's exactly what we did here, right? We took a basis. So this is purely from VC star, and this is purely from VC bar star. And so this basis for, which is a basis for V star cross C, is uh, is a union of these two, right? So we literally have a basis that is decomposed in terms of these two subspaces. So what does J star look like in this basis? So first of all, let's write this out. So V star cross C is isomorphic to VC star O plus direct uh, sum with VC bar star. In this basis L, um, we find that J star L is equal to, so okay, one caveat here, which is the order of the eigenvectors matters. Remember last time we were talking about the fact that um, the eigenbasis is unique up to a reshuffling of all of the basis vectors. So let's say that I had this basis. This is, well, I'll call them epsilon because we're talking about the covector basis. But imagine that we flip them around, and this was epsilon 2 and this was epsilon 1. Well, then all of your, I mean, you could do all of the same geometry with that. It's just that the label 1 and the label 2 have been swapped. But because we tend to order the matrices in order of the numbers, so then the matrices in this space would be flipped with respect to matrices in this space. So up to an difference in ordering. So we're going to normalize the ordering. We're going to put all of the i's in the front, and we're going to put all of the minus i's in the back as a diagonal matrix. So it looks something like this. Dot, dot, dot. And then at some point, there will be the last I, and then we start the minus i's, dot, 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 minus I. Right? So we can draw this in what's called a block diagonal form, where I'm going to say that this is a block diagonal matrix, or this is a submatrix, and I'll explain what these mean. So 0, 0, and then minus I. So this is the identity matrix, identity. And this is the zero matrix. The way you read a block diagonal matrix is you kind of separate it into all of the zones, and you say, okay, well, we know that this is an M times M matrix. So this is already, you just substitute, you paste in whatever matrix is being talked about. So instead of the identity matrix, it's I times the identity matrix, which is exactly what we have going on over here, right? This is I times the identity matrix. And then there should be an M of these as well. Remember, they always come in pairs. It's an even dimensional space. So half of them are going to be from one dimension. Sorry, half of them are going to be one eigenvector, and half of them are going to be the other eigenvector. So, so this one is minus I times the identity matrix. And we know that there are only zeros here. So we can represent this block of entries as the zero matrix. So that's what this means. So this is the form of J star in the eigenbasis. It's in its eigenbasis. Which we kind of already knew, but it's also nice to see that it works out. Okay. We're going to have to go slightly over time today because we have two results left, and it wouldn't be very neat for us to like push this off to next time because that would be a very short session. But let's try to get through these next two results. But these are very important. So, um, firstly, we would like to, because this next one is what we've been working towards the entire time. And this kind of completes our proof of the fact that uh, the two definitions of complex vector spaces are equivalent. So we said that one complex vector space, let's call it a CVS, complex vector space is a real vector space plus a complex structure. And secondly, a complex vector space is a vector space, just the definitions of a vector space over a field C. So these two are equivalent, and one of the things that we said in that proof is that what if we treat W the complex vector space, we restrict its scalar multiplication to just scalar multiplication by real numbers, and then treat it like a real vector space. And um, Orno pointed out that, well, can we do that? And this is the theorem that will say that, yes, we can do that every time. And um, and so this kind of completes that proof and makes it, let's say, watertight. So let's talk about that. Complex eigenbasis, which is what we had so far. It's L, curly L, induces a real basis. I haven't really been writing theorem so far, but um, yeah, theorem. Okay, let's say that lambda j. So we're now talking about, let me back up a little bit and set things up. So V is a real vector space. We have L. Uh, maybe I don't need to. Um, well, let's rewrite it. Lambda j, lambda bar j, where j of j star again, j star of lambda j is equal to I lambda j, where 1 is less than j is less than m. That's our basis L. It's an eigenbasis for um, V star O cross C. So what we want to show is that there exists uh, a vector basis for V of 2m real basis vectors and a covector basis for V star of 2m real covector basis covectors. Um, well, we know that V and V star will obviously have bases because they're vector spaces, and as long as we have the axiom of choice, we can always choose um, a vector basis for them. Uh, but what this specifically this there exists means is that there exists a basis that's induced. Let's say there exists an induced vector basis. So, all right, let's start with the proof. So we start with the fact that we decompose lambda j, and this time we're not going to use alpha and beta. We're going to say this is equal to epsilon j plus I epsilon m plus j. So this is going to be, I don't know why I switched the way that I write epsilon. We can just write it like that. Um, yeah, this is going to be just indicative of what uh, they're eventually going to be, which is the basis covectors. So we know from the definition that lambda j, uh, j star acting on lambda j is equal to j star acting on epsilon j plus I into j star acting on epsilon m plus j, which is equal to I lambda j. Remember, lambda j is from uh, uh, satisfies this equation. So therefore, we can write this is equal to j of j star. Well, it's the same thing. So I'm just gonna write that. We haven't done anything on the other side yet. Um, I epsilon j minus epsilon m plus j. So now we've applied them. Okay, so here what I've done is I've taken lambda j and I've expanded it out into terms. That's what we've done here. And then we've multiplied out everything. So then that's equal to j of epsilon j plus I j. It's the same thing, epsilon m plus j. So then we equate the imaginary and the real parts like the last time we did it. That gives us j of epsilon j is equal to minus epsilon m plus j, and j of epsilon m plus j is equal to epsilon j. Notice also that epsilon j is equal to this is standard for extracting the real and imaginary parts of uh, of a complex number. So we can do something like that. And to get m plus j, which is the imaginary part, we can do something like this. Where remember that in L we have lambda j and we have just as many lambda bar j's. So and each of these we have m of them. So what we're doing here is we're pairing them up. We're pairing like we're pairing lambda 1 with lambda bar 1 and so forth up to lambda m and lambda bar m. So this gives us the real and imaginary parts. But notice now that epsilon j and epsilon m plus j are linear combinations of all of these, right? So this means that if, right, let me just take a quick look here. So yeah, so let's say that we're going to call this B star. B star is epsilon j minus j epsilon j. So let's not be cryptic here. This is just epsilon m plus j, which I've written in the notes as minus j epsilon j. Yeah, and then the index runs from 1 to m. So this set is a linear combination of the previous basis set. So it's also a basis for all of B star cross C. Right. And so then so constructed we've constructed the real base the covector basis. So B star is a basis of 2m covectors. Since we've already called something B star, maybe we should call this, I don't know, let's call it C star. I don't know how to draw a curly C. There you go. That looks like a zeta. C. So that's our new basis. What we have left to do is to construct a basis for um, the the vector space. So let's do that next. So it's very similar to the previous one. Um, is it? No, actually, it's not. Let me explain this. So firstly, what we find is that if we're going to use see here is where we use the biorthonormality condition. Um, so what we've been using it a few times. I just didn't mention it, but this is one of the main times that we're going to use it. So here we take these two and we take their inner product. Now here's an interesting thing. Um, A is goes from we're saying that A goes from 1 to 2m. So we're saying that it goes over the entire spectrum that we've been looking at. So remember that our real space is like twice the dimension of our complex space. So in order to encapsulate both like epsilon I and epsilon m plus I, we're going to take A to go from 1 to 2m. So this is defined to be J of EK, and then, yeah. So again, we're using the definition. We're moving the J star to the other side, just turns it into a J. Break it down in terms of matrices. I don't think I put the basis down for this. EL, uh, comma, epsilon A, which gives us, so we're taking out that coefficient, J, K, L, EL, epsilon A is equal to, so the basis is the eigenbasis. We can just take it as the eigenbasis. I'm not going to repeat it here. Mostly because it's easier for me to um, repeat the proof if I can just copy it. EL epsilon A. And we know what this, did I just write the same thing right? So we evaluate this term and this term, again, with the biorthonormality condition, gives us delta LA, which means that this whole thing, so again, we collapse the Kronecker delta into the indices, which gives us J, K, A. Now, the next part is the interesting part. Uh, let's say that if A is equal to L, where L is an index that goes from, sometimes I write this like that. A is an element of 1 dot 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 M. So this is so L is an index that goes through half of the range, the first half of the range. Then what we get is EK J of epsilon L Well, we know what this is, right? We've already figured out what J, or this should be J star. Notation's catching up to me again. So these also, so these should be J, right? That's fine. So we know that this is minus epsilon m plus L from the last time. We saw that J star of epsilon J is equal to epsilon m plus J. So J runs, but M doesn't run. M is a constant. M is the dimension of the manifold. Okay, so, and we can take, we know that this is, again, we use the bi-orthonormality condition, delta K uh, M plus L. So that means that, so then we can do an interesting thing, which is that when A is equal to L, then J of KL is equal to minus delta K M plus L. And so M doesn't have to be on the other side because M is a constant. The only indices are L and K. This tells us, so while I write this, let me explain something, um, since this is somewhat boring. Um, the reason why you see that a lot of these proofs start with the covectors and then move on to the vectors is because I think it's because Ternchen and Lamb also define covectors first and then define vectors. So they're always doing they're treating the covectors as the fundamental ones, and then they're treating the vectors as the dual to the and so or maybe it's just convention. Um, they always like to do it in the same order. That's why you're seeing them in the same like first we prove it for the covectors, then we prove it for the vectors, and so forth. And then the second one is pretty similar, so I think I'll skip the second one. Here I'll just outline that if we say that A is equal to M plus L, then we get that J of K uh, L, right? Where if we equate the two sides, then we get this. And then if we take J of E M plus L, we're doing this strategically. We're doing this strategically. Sorry, this should be K. So we're doing this strategically. We did this because we know how to decompose these in such a way, right? We know that we took, okay, this is a subtle point in this proof, so let me explain. The reason we evaluated J of EM plus L might actually be a little confusing here, because where did this come from? Why did we choose to evaluate this? It definitely gave us something. It gave us what J of EM plus L is equal to, which is minus EK. But how did we know to do that? So that's interesting. Um, we saw that we found an expression for the matrix elements that included M plus L. Since it included M plus L, and we know that J transforms our M plus L into um, right, JL is associated with M plus L. So we knew that if we substituted this, then we would get an M plus L over here, which makes our math really easy. This is what we were after. Since since these two indices are the same, we can just replace this with K. That's what we did here. That's why we started with EM plus L. And that's why in this one we start with K, because we have an L over here. So we don't need to do that. And that cleanly gives us the two relationships, which this one will eventually give us minus delta M plus K L. Sorry, I was copying this off of the wrong part, but yes. So then this will give us M plus K L, and we will get EL. And so again, see, these two match up now. And so then we can replace this with M plus K, which gives us a relationship between EK and EM plus K. Which you could just think of these as um, EM plus K. Did I get that right? minus delta. Oh, the minus is not supposed to be here. Yeah, typo in the notes. So delta m plus k L E L gives us em plus k. So which gives us the other result, which is that j of ek is equal to em plus k, and j of em plus k is equal to minus ek. That's how it works. So you, these are not strictly necessary for this result, but you could think of these as sub-results, which are these are also interesting. And if we go back to the previous one, we got these as well. These are the covector versions. So these are important as well. These are interesting results. I'm going to highlight this. But then let's shuffle everything a little bit up so that I can talk about the next thing. Right. So we call this B in the notes, but I'm going to call it C. There we go. C, little curly Q C. Um, this is our new vector basis, very similar, EK, EM plus K, where 1 is less than K is less than M. And you can also write this as, I'm going to write it here. You can write this element as J of EK. I think I removed it from the notes maybe, but part of the statement here was that you can write this, the basis that you get, you can write it in this form. EK, J of EK. And the covector basis, you can write it in this form. Minus J of epsilon K. And there's some stuff here that I'm not writing. But yeah, so these are the two bases. Each of them have two M objects in them, right? So this is M objects and this is M objects, and this forms a basis. And that's the basis that we're guaranteed to have and be able to move from the um, complex space to the real space. Wait, layer is invisible? Okay. Okay, the last thing that we want to talk about today is when is the complex structure on a vector space unique. So we're not going to get into every situation in which it's unique. I don't know for a fact that this will guarantee it, but this is a condition that will make it so that it is unique. So let V be a vector space of dimension n equals 2m. Uh, they're saying, so this is the theorem. If V star cross C can be decomposed as VC star plus VC star bar. Well, we know that it can always become decomposed like that. So what are they saying? In such a way, in such a way as to have a one-to-one correspondence, which is complex conjugation. So why did they say it that way? Let me explain. Um, I mean, we kind of because we said that, okay, well, we did all of that analysis. We named VC star and VC star bar a very specific space. We kind of are presuming that we know what VC star and VC star bar are, but what they're really saying is like, what if it was A plus B, right? Um, I mean, VC star and VC star bar are both um, they're both spaces of they're just labels. We have no idea what the label means. The labels are only significant if uh, my computer froze. Um, Let me wait for that to. Okay, I think it's back. Okay, let me continue explaining. So, um, A and B are two separate spaces, and so we know nothing about A and B other than the fact that they are uh, like that V star cross C can be decomposed in terms of A and B as a direct sum. So what they're saying is plus, okay, so it can be decomposed as a direct sum B, but also A and B have to be related to each other by complex conjugation. Oh, my pen is no longer working. That's going to be a little tough. Uh, let me see. We're gonna have to do a little bit of tech support in the middle of this. Let me see if I can fix that. It says device is connected. Okay. I'm a little scared to turn off the screen, but maybe that will work. Okay, it's back. Good. All right then. Sorry for the interruption. Uh, right. Let's continue. Um, so yeah. So they're not just A and B, right? They're very specific spaces, and we name them such because they're related by conjugation. So, um, in this situation, there will always be there will always be a unique linear map. We'll call it J, um, that acts as a complex structure. That's all you need. You need V star times C to be decomposable as a direct sum of two spaces. We don't know what those spaces are, other than the fact that if you conjugate one and you get the other, then then the complex structure must exist. Okay, so let's first of all let's hypothesize. Okay, so this should be J star. Did not change all of the J's to J stars at all. So V star cross C goes to V star cross C. So then we say, like, let's define this as J star of F oh, I used F again. Let's say phi. J star of phi is equal to I phi if phi is an element of VC star and minus I phi if phi is an element of VC star bar. And because we know that VC star and VC star bar, we can add them to get any element of V star cross C. Therefore, we can always decompose phi into, again, like phi 1 and phi 2. And then if we do that, then we can use this definition on the phi 1 part, we say it's I phi 1, and on the phi 2 part, we say minus I phi 2. So this works for any element in V star cross C. Um, so then, yeah. And now we consider the basis L such that uh, epsilon j is equal to half lambda j plus lambda bar j, and epsilon m plus j is equal to minus I by 2 lambda j minus lambda bar j. I think I missed the I in the last one, maybe. Uh, yeah, I might have missed the I in the last one. Oh, anyway, so we know that, so right, we have the eigenbasis, right? And we've constructed these vectors from the eigenbasis. We still don't know what they're like. So we're going to test that. So if we apply J star on epsilon j, what happens? We get half uh, I lambda j minus I lambda bar j. That gives us minus epsilon m plus j, and J star acting on epsilon m plus j equals to minus I by 2 I lambda j plus I lambda bar j. That will give us epsilon j. Lastly, yeah, so we needed these to decompose. So let's say we have a generic covector alpha. So we can always decompose that as this. So we're moving to that 2m dimensional real basis. So on am plus j epsilon m plus j. So then if we, so basically we don't know yet, right? So um, we're saying that there will be a complex structure, right? So what we're trying to prove right now, I should have said this at the beginning. What we're trying to prove right now is that there exists a complex structure. So yeah, so we need to show that J star squared actually gives us minus alpha, right? So that will prove to us that a complex structure exists. So then that is equal to J star squared of alpha j epsilon j plus I alpha m plus j epsilon m plus j, which is equal to alpha j star squared of epsilon j. So we're using linearity plus alpha m plus j star squared of epsilon m plus j, which is equal to, we'll cut to the chase, we'll apply both of them at the same time. Uh, yeah, so that ends up with alpha j star of epsilon j plus minus alpha m plus j star of epsilon m plus j, and that ends up giving us minus alpha j. Sorry, this should be here, and this should be here. Because j star swaps them, right? J star swaps these two. Um, and so we get this. Which is the negative of alpha. So we've shown that j star squared is of alpha is equal to minus alpha, which is what we wanted to show. This means that uh, j star is right. J star squared is equivalent to minus identity from v star cross c to itself. I'm not going to write it again. Right. So that shows that it is indeed a complex structure. We started off saying that J star is just a linear map from V star. So we made a definition and then we broke it down until we could show that J star squared of alpha is equal to minus alpha, which means that we do have a complex structure on this space. So home stretch, we just need to prove that uh, it's unique. So the second thing that we need to prove is that J star is unique. How do you prove that? So, and one interesting way that we could prove that J star is unique is that um, let's say that we assume that we have another complex structure. Um, we'll show that that other complex structure exactly is the same one that we defined. So J star of phi, when we defined it in that piecewise way, I of, let's call it phi 1, if phi 1 is an element of VC star, and minus I phi 2 if phi is an element of VC star bar, will show that no matter what you do, no matter like as long as you assume that J star is a complex structure on V star cross C, then you by uh, that fact alone, it will have to have this action. So that means that there's only one possible complex structure. So that's where we're going to try to show. Uh, okay, so let me see how we're doing this. So we have that J star. We know, so now we're assuming that J star uh, is a complex structure. So we start with this. And we know that there's an eigenbasis, which I'll just call it L. We also know that J star acting on lambda J from this eigenbasis is equal to plus I lambda J. We know that J star acting on lambda bar J is equal to minus I lambda bar J. Uh, and so let's see what happens. So we also know that these are bases. Bases. So, okay, let's say it like this. So these are both bases, but this is a basis for VC star, and this is a basis for VC star bar. So we know that if this is true, right? If we get so the next part of this is a little bit of a subtle point. So this is a basis, right? So this is what it acts like on the basis vector. So then what we're essentially proving in the last part is that if I have any generic vector, let's say that J star is acting on any generic vector, which is a linear superposition of these basis vectors. Let's say that uh, alpha alpha j lambda j, right? Then this will be equal to uh, alpha j. So exploiting linearity, j star of lambda j, which is equal to alpha j into I lambda j. But then the I can just come out, and then we just have this, which means that we can transfer it onto the entire vector. So as long as it's true for the basis vectors, it's true for any arbitrary linear combination of the basis vectors. And so same thing with the other subspace. So this is for VC star, and if we can do the same thing for VC star bar, this will be equal to beta j, j star, acting on lambda bar j, but we know what it does on lambda bar j. It multiplies it by minus I. We can take that minus I out to the front. That gives us the original vector back, which means that this is just equal to minus I. If we call that vector covector beta, then we get this. And if we call this alpha, then we get I alpha. So we've shown that, what does this mean? This is interesting. So this means that as long as alpha is an element of VC star, its action, J star's action on uh, on alpha is equal to I times alpha. And as long as beta is an element of VC star bar, its action is minus I beta. And that's necessitated by the fact that this is an eigenbasis. And because VC star and VC star bar are uh, always exist, and their bases are always these bases because they are the eigenspaces of J star, that means that these always exist. These are necessarily true. And since VC star and VC star bar are related by complex conjugation, they fulfill the what do you call them? The prerequisites for the theorem. So therefore, we know that J star, as long as it's a complex structure, it must fulfill this, which means that it must fulfill this, which means that since these are complex conjugations, it fulfills the uh, prerequisites of the theorem, but that means that anything that's in VC star will be acted as I alpha or will be multiplied by plus I, and anything from VC star bar will be multiplied by minus I, which means that we just showed that the action of J star, as long as it's a complex structure, is exactly the definition. So there's only one complex structure. It's the one that looks like this. And so we've proven that J star is unique. So as long as there are two spaces, so these are the prerequisites. V star cross C has to be decomposable into A plus B, where if we take the conjugate of A, or like what I'm trying to say is, let's say A is an element of A, then A bar is an element of B. That's what I mean. So then that's what I mean when I say A bar is equal to B. Um, so and that's true for all. Yeah, you get a B in an element in B for every element in A and vice versa. So they're related by conjugation in a one-to-one correspondence, then uh, you will always be able to find a unique complex structure. Okay, and that's the last result. All right, so we've taken a good bit of time, but I think it saves us from having a session that's 10 minutes long. So let's summarize what we did so far today. Summary. I don't know why I off-center it so much. Summary. Okay, so we looked at some interesting results. I think the first one that we did today was we showed that um, J stars matrix in the dual basis is J transpose, right? That's the first thing that we showed. Whatever J's um, basis is, J star's basis is assumed to be the dual basis to that. Number two, we showed that J has two eigenspaces. That being VC uh, star and VC star bar. And this corresponds to plus I, this corresponds to minus I. And they're related by conjugation. Three, we showed that any V element of V star cross C can be, well, let's just write it like this. V star cross C is isomorphic to VC star uh, direct sum VC star bar. So you can express any element from VC star cross C as one element of VC star plus an element of VC star bar. So, right. And then we saw that the form of J star in the, uh, yeah, so from here, or from here, we got the eigenbasis, L, which looked like lambda J, lambda bar J, uh, such that lambda J star of lambda J is equal to I lambda J. And in this basis, this looks like the block diagonal form plus I identity 0, 0, minus I identity. And it doesn't need to be this way. Um, Based on the way that we ordered the basis here, if you think of it like, okay, we have all of the basis vectors that correspond to plus I at the front and all of the basis vectors that correspond to the minus I at the back, then it'll look like this. But if you mix them up, you'll mix up some of the plus I's and minus I's. That's not very important. Or like the point of clarification is important, but the order is not important. Okay. So, and then we looked at one of the really important takeaways, which is that uh, the complex eigenbasis L can be used to induce a real basis for the covectors covector space and the vector space. Lastly, we saw how we can ensure that there exists a unique complex structure on a space, on a complexified space V, V star C. Okay, so, and that, uh, in order to do that, we said that, okay, well, V star cross C has to be decomposable into A plus B, and A and B need to have one-to-one correspondence via conjugation, which V star C and V bar star C both like together they satisfy that. All right, so that's what we did today. So um, before we conclude, I'd like to ask people if they had any questions on what we did or maybe clarify something, comment on anything. Okay, I'm gonna open the chat and we'll see what happens. Gonna pull it up on my other monitor. Okay, I'm gonna wait for questions. I'm just gonna have a quick drink of water. All right, if there aren't any questions, it seems like there aren't, then let's just give a brief sneak peek on what we're gonna do next, and then we will call it for today. So next time, we will be doing complex vector bundles or vector bundles, and then we're going to make them complex. And this is where the notion of um, I'm not sure if this is what they're called in math, but they're called this in physics, vector fields. This is where they're going to come from. These are called sections on vector bundles. And they're going to be necessary for defining a lot of things in the future. So this is kind of a setup for some of the things that we're going to need in the future. Um, and we're going to do a few of those until we get to Riemannian geometry, which is going to be about the geometry. Remember, we were talking about the fact that we have complex differential geometry. So we've covered the differential part and we've covered now the complex part. Um, and so like the differentiable structure, and now we have the complex structure. And in order to be a fully geometric space, we'll need a metric. So we'll look at that metric structure then. And then once we're done with that, we'll look at some complex differential geometry specific manifolds. We're going to look at the Kähler manifold or the Kähler manifold. We're going to look at permission manifolds. That might be in the opposite order. I don't remember exactly. Um, and we're going to look at the very famous Calabi-Yau manifolds. In the middle, we're also going to look at this is becoming a sneak peek for the rest of all of the course. So, Dobald cohomology group. So, yeah, and then Riemannian manifolds. So that's kind of what we're going to do next. But immediately next thing that we're going to do is we're going to look at these. We're also going to look at exterior algebras and orientations on vector bases and stuff like that. So that's it for today. Thanks to everybody for coming. Um, we'll hope to see you next time. Gonna stop the recording.